Welcome to the first lecture for the course of Fourier analysis. This is going to be an introductory lecture, and where we will find the origin of the Fourier series, and what are the we will discuss about prerequisites we need for this course. So, first, this is Joseph Fourier, so who had initiated study of Fourier series and which has profound impact in mathematics, in every sphere of mathematics. So, this is the picture of Fourier. Fourier was born in 1768 in Auxerre, France. He was ninth child and was orphaned at the age of 10. The French Revolution prevented Fourier's desire to enter the Benedictine teaching order, which was basically reserved for elite people, and Fourier was a mathematician and physicist and is renowned for his groundbreaking contribution to the study of heat transfer and mathematical analysis. His famous work on the Fourier series revolutionized our understanding of periodic functions and paved the way for numerous applications in science and mathematics, as well as in engineering. So, let us see first, all of us we know about the heat equation. So, the heat equation is given by del u by del t, some constant times del u by del t, del square u by del x square plus del square u by del y square in the plane for some constant c. So, when the heat exchange stops reaching the thermal equilibrium, that means del u by del t is equal to 0, then this equation, the state, it is called the steady state equation, and is obviously given by del square u by del x square plus del square u by del y square is equal to 0. Now, if we are looking the heat equation on the unit disk, that is this is 0 0 and this radius is 1, the unit disk, this is less or equal to 1. If I take the d is, this is less or equal to 1, then this is our unit disk, which we can write it in terms of the polar coordinate. So, now if in the unit disk, if we are taking any point here, then this is going to be can be represented by the radius, which is r, and then this is theta. So, that essentially is, now r can vary from 0 to 1 if we are taking the open unit disk, and which means the boundary is not there, and then the Laplacian is defined as delta is equal to del square u by del x square plus del square u by del y square. In the polar coordinates, the Laplacian is going to look like del square u by del r square plus 1 by r del u by del r plus 1 by r square del u square by del theta square. And this you can easily derive by making the x coordinate in the Cartesian x coordinate as r cos theta and y coordinate as r sin theta, then apply the rule of the differentiation, and what easily with little bit of patience you can compute that Laplacian is going to look like this. So, the steady state heat equation means delta u, the Laplacian of u is equal to 0. Okay, so, now that is what we want to now solve this problem. So, now when delta u is equal to 0, so in polar coordinates you can see that del square u by del r square plus 1 by r del u by del r is equal to minus 1 by r square del square u by del theta square. If you multiply r square on both the side, what you are going to get is this equation. So, now let us make an attempt to solve this equation by using the separation of variable. So, let us assume that the solution of this can be separated in r variable as well as in theta variable. So, let us assume that if our solution looks like u r theta equal to f r in g theta, then what is going to be the value of f and g. Okay. So, now if I take the derivative with respect to r variable, then we are going to get f prime of r, because now f is a function of r. So, this is f prime of r into g theta, and if we take the second derivative with respect to r, we will get f double prime of r g theta. Now, if we similarly if we take the derivative with respect to theta, then f is not going to get affected, and hence we will get the derivative with respect to theta will be transferred to g, and to distinguish between the derivative with respect to r and theta, I am writing the symbol g double dot theta means del d square g by d theta square. Okay. So, therefore, we have by this equation, if we put it, then we get that this is r square f double prime r plus r f prime of r divided by f r. This is equal to minus g double derivative with respect to theta by g theta. Look at the both the left and right hand side. Now, the two sides are of different variable. Left hand side is independent of theta and the right hand side is independent of r. Therefore, this ratio is going to be a constant. So, what we get from this is equal to lambda means g double derivative with respect to theta plus lambda of g theta is equal to 0, and in if this is equal to lambda, r square left hand side is equal to lambda, then we get r square f double prime of r plus r f prime of r minus lambda f r is equal to 0. Since we are in the disk and this theta variable is 0 to 2 pi, and then g is going to, as a function of theta, is going to repeat after each 2 pi interval. So, we call that to be a 2 pi periodic function. In this course, we will discuss a lot more about the periodic functions at a later stage. In this introductory lecture, so I presume that you understand that 2 pi periodic means this is going to repeat after 2 pi. So, and now if we take lambda to be lesser equal to 0, then one can easily see that what we are going to get is trivial solution. Therefore, we assume that lambda is greater than 0. Now, that means lambda, and it has to be an integer. So, lambda equal to m square for some m belongs to z. Therefore, what we got is that if we solve this equation, then what we got is g theta equal to a tilde cos m theta plus b tilde sin m theta for some scalar a tilde and b tilde. Now, we know the Euler's identity e to the power I theta is equal to cos theta plus I sin theta. Then we have, if we plug in, we can write g theta equal to a e to the power I m theta plus b e to the power minus I m theta for some constant a and b. Now, lambda is equal to m square. So, we need to look at what is going to be the form of the solution capital F, the function. So, we have this equation r square f double prime r plus r f prime of r minus lambda f r is equal to 0. Okay. Now, if m is not equal to 0, then f of r is equal to r to the power m, and f of r equal to r to the power minus of m. So, this is, if I plug in r to the power m, you have m into m minus 1 r to the power m minus 2, you multiply this, you get r to the power m, here you are having m, and so this is equal to 0. Now, if m is equal to 0, then obviously f of r equal to 1, this is going to give us a solution, as well as it can give a solution that f of r is equal to log r. If you take the double derivative, then easily one can verify that this satisfies the equation here. That is easy to see. Now, if m is greater than 0, then r to the power minus of m goes to infinity as r goes to 0, because this is going to be 1 by r to the power m. So, when r goes to 0, this is going to be infinity, and if m is less than 0, then r to the power m goes to infinity as r goes to 0. So, that is why if m is, and if m is equal to 0, then log r also goes to infinity as r goes to 0. And remember that we are looking for bounded solution. Therefore, for each m belongs to z, we get that we can discard this. So, we get u m r theta equal to r to the power mod m e to the power I m theta. Now, what is the claim of Fourier? The general solution, what we get is u r theta. For each m we are getting a solution, and this is a linear equation. So, we get the general solution, we can write that m equal to minus infinity to infinity a m r to the power m e to the power I m theta, and where a m is a scalar. Now, you can see that if for each fixed r, if a m is a bounded, if a m is lesser or equal to some k for all m belongs to z, then this series converges, and that is what is going to be the general solution of the heat equation, steady state heat equation. If this, now remember that we had assumed that if our solution looks like f of r g theta, then this will be of this form. If this gives all the solution to delta u equal to 0, that means what we are saying, that if we have a solution of the heat equation, steady state heat equation, then it must look like u r theta is equal to f r g theta. Then in this case, if I put in the boundary where r equal to 1 is the boundary of the disk, then u of 1 theta is equal to a m e to the power I m theta, which is a function of theta, no more dependent on the radial variable. So, now this is a function which is defined on the circle. So, given any reasonable f on 0 to 2 pi and which is f of 0 is equal to f of 2 pi, that means we are talking that f is a 2 pi periodic function. And now the question comes that can we find a m such that f of theta equal to a m e to the power I m theta. So, this is what Fourier claimed that if we have a function on 0 to 2 pi, then which is periodic, then this f of theta can be expressed as m equal to minus infinity to infinity a m e to the power I m theta. Of course, now this raises many questions. First of all, that given a f, what are these a m? Can we determine this a m? That is the first question which Fourier answered. Like if for the time being, if you allow me to do certain calculation in without caring about mathematical rigor, then you can see that 0 to 2 pi f theta d theta, this is equal to, suppose this expression holds 0 to 2 pi summation over m a m e to the power I m theta d theta. Now, if I am allowed without bothering that whether what is the condition that we can interchange the sum and the integration, if we just formally do this 0 to 2 pi, then this a m is independent of m. So, we get e to the power I m theta d theta. Now, this integral we know that this is equal to 2 pi if m is equal to 0 and is equal to 0 if m is not equal to 0. Therefore, we get this as 2 pi of a 0. Now, in the same way, if we write down 0 to 2 pi f of theta e to the power minus of I n theta d theta, then this is equal to, without caring about how to change the summation and the integration, we just, if we do it formally, then this is going to be 0 to 2 pi e to the power I m minus of n theta d theta, which is, this integral is going to survive only when m is equal to n. Now, remember that here we are taking the n, a fixed n. So, this is equal to 2 pi of a n. So, without caring about the correctness of all these mathematical ideas we have employed, I mean, if we forget, if you grant me that I have all the freedom to interchange the sum and the integral, then we know that given a f, how to determine a m. But all these steps need to be justified mathematically, why all these steps are valid steps. Then the second question obviously comes that this is an infinite series. Now, what is the guarantee that this infinite series will converge? Then the next one would ask, even if it converges, suppose I have a m which are denoted by this formula, and suppose this infinite series converges, then what is the guarantee that this infinite series is going to converge to the original function f what we have started off? So, these questions are very deep, and in the course we are going to address all these questions one after another. So, before getting into more rigorous mathematics, so let us first recall our what we have learned in the topic of infinite series, and we will be needing, here we are talking about the integration. So, we will be needing about certain properties of Riemann integration. So, let us first review quickly what we have learned for infinite series. That is the first one. Okay. So, by infinite series, what does it mean? Because we know that we can we have an algorithm where we can add finitely many terms, but when it comes to infinite, then we have to be very, very careful. So, what we do is that we take the partial sum S n, which is n from 1 to n, a n. Now, this becomes a sequence of real numbers if I am taking a n in R, and if a n are complex number, then S n is also a complex number. Okay. We say that the series, this series converges to L if the sequence S n converges to L. Now, the sequence is some partial sum of a n's, which are real or complex number. So, we know a sequence of real or complex number, what is the meaning of convergence of a sequence. So, if this partial sum, this sequence converges to L, then we say that the series we have started of converges to L. So, what is the meaning of the convergence? That means, as usual, just recall that for a given epsilon, there exists a n sub naught such that mod of S n minus of L is less than epsilon for all n greater or equal to n sub naught. So, now to write that formally, that is the series A n converges if and only if for epsilon greater than 0, there exists a n sub naught such that the tail of the series n equal to k to m a n is less than epsilon for all m greater or equal to n greater or equal to n sub 0. As you can see that if I am taking S m minus of x k, if S m S n is a Cauchy sequence, then this is less than epsilon, and that is nothing but what we are writing. This guy is n equal to k to m of a n. So, every convergent sequence is a Cauchy sequence. So, therefore, what we have got is this, that is an if and only if condition. If the partial sum is a Cauchy sequence, then it converges, because R is R or C, they are complete. Now, if A n converges, if the series converges, then we know that the nth term they go to 0 just by this, because this S n minus S n minus of 1 is equal to A n. Then from the above we can see that the nth term converges to 0, and this is a necessary condition of a series to be convergent. This is far, far away from being a sufficient condition, that all of us we know that n equal to 1 to infinity summation over 1 over n, it diverges. Okay. So, so far so good. Now, to test the convergence of the series, which we are quite familiar with, and now if most of the tests what we have learned, they are valid for if our ANs are non-negative. One of very favorite and most useful among all the tests is the comparison test. That means, we have a series which converges, and that series consists of non-negative terms B n. Now, we have A n which are also non-negative, and for each n this is less or equal to some constant times B n, and this constant is independent of n. So, this is true for all n, and if B n converges, then A n converges. That means, if I have the series of non-negative terms and which is dominated by a B n which is a part of the convergent series, then our series is convergent, and this is a very useful test to figure out whether the series is a convergent series or not. Then as an application of the comparison test, that is some easier way to deal with, is that you can find that root test, that if mod of A n to the power 1 over n is equal to L. Now, if L is less than 1, then the series converges, L is greater than 1, then the series diverges, and if L is equal to 1, we can't conclude anything. And then the ratio test, as we are familiar with, again for the non-negative A n's, if limit of A n plus 1 by A n is equal to L, then and L less than 1 it converges, L bigger than 1 it is diverges, and L equal to 1 we can't conclude anything. So, I think this is a good point to stop with. Then we will see that what are the other kinds of tests in which we can conclude whether a series converges or not. Thank you.